team session on clinical trials now. The rest of the day, perhaps a part of from the very last talk. Before I let you talk, I just wanted to say that during this program we had week 1 where we had some talks on clinical trials by Stevenson and Mike Krams. And now we have the whole day devoted, almost whole day, so devoted to this particular topic. And Peter Miller actually helped us a lot to organize that, as he was our scientific advisor. So I'd like to thank you for your help in doing preparing this program and getting this really, like I say, big fishes here to get and speak. So for the moment, for this session, we have 2 talks, one by Peter Miller and one by Anthony Atkinson. And now you have your 25 minutes.
Thank you. Thank you for the opportunity to present here. I really appreciate it. I'll talk about specific clinical trial design and how to proceed with optimal design in that context, so-called random discontinuation designs. This is joint work with Lorenzo Tripper, a really smart graduate student from Bocconi, actually. Watch out for him, he'll make a good career. And Gary Rosner also at MD Anderson. Quick outline, I'll first introduce in plain English what these designs are about. I'll take a decision theoretic approach to it. So in order to fix the design parameters, I'll use a decision theoretic formulation which requires to specify the actual decisions that you have to make. You need a probability model and you need utilities, and I'll talk about it in all glorious detail. The probability model is actually very nifty and nice. I'll probably still run over it very fast because it's very problem specific. But then I plan to spend a bit more time on the utility function. For those of you who heard Mike Krams, he might have talked about similar things. I tried to chase it down online, but it doesn't seem to be there yet. And in the end, I'll show you some pretty pictures. I don't really have that much to say, so I'm quite sure it'll be in time. And also, please feel free to chip in as I go along. Yeah, like don't wait till the end. If it becomes too long, I'll tell you, let's talk in the end. So please feel free to comment as we go along. So the idea of the discontinuation design is it provides us a mechanism to essentially, it's an automated mechanism to identify a susceptible population. The notion is that in contrast to like chemotherapy or like some brutal treatment where kind of the more the better to kill the cancer, but you don't want to give too much, otherwise you kill the patient, which are quite simple because the poison works for everyone, kind of, yeah. There are now increasingly more treatment agents like we heard about it earlier this morning that target some specific mechanism that have like molecular targets. And there the notion is it's not necessarily going to work for everyone. It might only work for a subpopulation. Sometimes we know what subpopulation it could possibly work for. Sometimes it's not so clear. And when it's not so clear, then this design becomes quite nifty because it will allow us an automatic self-identification of patients who can possibly profit from that. And you'll see in a moment how the thing works. So what we do is, initially at time 0, all patients get treated with the experimental agent. So to start with, everyone gets treated by the experimental therapy. We wait a while. To be specific, let's assume that the goal of the therapy is to slow down tumor growth. We just want to control tumor growth. That's the intention. Then after some time, we just look at all the patients who were enrolled at time 0, and we see whether they have stable disease, means whether tumor size is within a certain window. If it is, then that patient is obviously a patient who could potentially benefit from the treatment. So, and if it's not, then the treatment doesn't work for that patient and the patient leaves the study. But if it does, then the patient could potentially benefit from the treatment, and at that time we randomize the patient now to either continue on treatment or to switch to control. So the whole idea is, in that first step, the thing proceeds by steps. In that first step, up to time t1, everybody gets the treatment, and you just simply make a judgment. Can you see any evidence for an effect, yes or no? If you can see, then the patient is self-identified as being in a susceptible population, and we randomize. If not, then the patient is not in a susceptible population, and he or she leaves the trial. And then we continue in the second step. In the second step, we have now randomized to two subgroups, treatment and control. And if the aim is to slow down tumor growth, then you might record at the very end at time t2, you record tumor size. You compare between treatment and control group, and the better one wins. Yeah, like then you just do like a standard conclusion like in a randomized design. So that's the idea in plain English. Same story in a picture. Here's time t0, the start. At start, everyone gets the treatment, everyone gets the experimental therapy. At time t1, you look, those patients who achieve stable disease, they get randomized to treatment and control because those patients are susceptible to the treatment. The therapy seems to work for them, or at least they respond to it. Those who do not show stable disease, they just leave the trial. That's the idea. One of the nifty features of that design, and that's perhaps more practical, pragmatic issue than anything mathematical, all patients get a treatment initially. It's always a slightly awkward thing to ask a patient to sign an informed consent form for a nifty new therapy, and you have to tell him or her there's a good chance you just get placebo. Yeah. So it makes it easier. It makes it easier to recruit patients if everyone has a chance to get the new therapy. It's a way to automatically select a subpopulation who could benefit from the treatment. That's important for targeted therapy, where it's not at all clear how you find a good subpopulation. Someone was talking about, Keith was talking about overcheck and overtest, right? So it's not always clear how you identify subpopulations, be it for one thing or be it for susceptibility to a new treatment. Or same thing in different words. The idea is the notion that patient populations are very heterogeneous. People come with all kinds of prior treatment history, all kinds of different biomarkers, all kinds of different baseline characteristics, and it's not obvious how we should select the relevant patient population. This is kind of a magic automatic algorithm to do so. In particular, it's sensible for so-called cytostatic agents rather than cytotoxic agents, where you just try to kill the tumor by essentially poison. Here what you try to do is you just try to slow down tumor growth by targeting some molecular target. So in principle, the story sounds good. Unfortunately, in practice, there's lots of caveats. There's a couple of recent papers who just report comparisons of randomized discontinuation design versus straightforward upfront randomization. Friedlin and Simon, they report that the RDD can have higher power in some scenarios if you're very careful in choosing the parameters. I should have pointed it out on the previous slide. The parameters that you have to choose is you get to set the T1, like how long do you wait until you make the first decision. You get to choose the T2, how long do you wait for the final conclusion. And you obviously get to choose the sample size. Fedorov and Liu, they also show, again, some advantages. So it's not a magic thing. It can work depending on how exactly you set it up. Or even worse, Capra show for with a time to event outcome, it actually turns out that in their particular setup, this is always specific to the kind of scenario that you assume, in their particular setup, it actually turns out that simple upfront randomization has higher power. So you don't win anything. On one hand, that's sad. On the other hand, that's a feature for us because the bottom line being it's important to get the parameters right. It's important to fine-tune the design correctly if you want to achieve anything, which means there's really something to gain by careful optimal design rather than just eyeballing it. A couple of recent trials that actually ran with randomized discontinuation designs. So far for the characterization of these trials in plain English, the idea is clear, right? It's kind of, in principle, I like the idea. It's kind of a really nifty idea to, rather than trying to specify the eligible patient population by trying to guess what kind of patients will be benefiting from the treatment, having a mechanism that self-identifies patients who could benefit. So as I already mentioned, the design has like three design parameters. There are three knobs to fine-tune. Sample size, T1 and T2. In particular, if the T1 gets too large, like if you wait too long, if our rule to identify the patients to randomize is stable disease, if you wait too long, then all of them will have progressed and we don't randomize anyone. If the T1 is too short, if we don't wait long enough, then there is no selection, yeah? And you might not find anything. So you want to be somewhere in between, and it's not obvious what's the right choice. It's a classic setup where formal optimization can actually achieve something. If you include T1 equals 0 as a possible choice, then you automatically include as a special case a simple upfront randomization. T1 equals 0 means you skip the first step and immediately randomize. So that way, the optimization will even include a comparison with simple upfront randomization. If you allow n equals 0, then that includes a possible recommendation not to initiate a trial if things don't look good enough that you might stand to gain anything. And so these are the n, T1, T2 are the decision parameters. Those are the those three guys index the decision. We'll need a probability model. The outcome that we observe, indicated here as boldface X, the outcome is simply tumor volume over time. So for each patient, we record tumor volume over time. Phi, I'll just use generically for the parameters. So I owe you a sampling model for the observed outcomes. Details are coming up, although I'll jump over it fast because it's problem specific. And I'll need a decision criterion. We saw quite a few over the last few days. So what comes here is like a decision criterion, something like the ethical criterion or something like the d-optimality, and it's yet another one, but in a similar spirit. The nice thing is that I'll only have to bother writing down the decision criterion for hypothetical assumed future data, like if an oracle tells you the future data, and if you were to know the parameters and consider a certain decision, then I'll ask you to tell me how much it's worth to you. Yeah? I will talk in detail about that in a second. I'll use small u for the decision criterion. If we are willing to write down a decision criterion for a contemplated decision, hypothetical parameters, and possible future data, then obviously the optimal decision, obviously the optimal thing to do is whatever maximizes the decision criterion, right? In doing so, though, there's an embarrassing detail. The decision criterion includes two things that you don't happen to know, right? And that's where you can do a variety of things. You could plug in, or you can argue from first principles that a rational decision maker should proceed by maximizing that utility in expectation, where the appropriate expectation is with respect to all unknown quantities and conditioning on whatever is observed at the time of decision making. In this case, I don't assume that any preliminary data is observed, so we integrate over everything. In particular, we are marginalizing over the future data, and we're integrating over the parameters. So this is simply the expected utility maximization paradigm. And you can argue that this is the way to proceed if you want to act rational in a certain sense. I invite comments or complaints, yeah? No? Bummer. Because, I mean, this is a bit different from other traditional, I mean, it's also very traditional in a certain corner of statistics, right? But it's different from just taking like the optimality, the information metrics, taking the determinant and maximizing that, right? In particular, I haven't yet told you what the utility is, but the utility will be a little bit in the spirit of the ethical criterion, like we'll try to specifically look at what actually happens with the patients. So what's coming up now in the remaining few minutes is I'll talk you through a probability model. I'll run over it because it's beautiful, but it's really problem specific, yeah? And then I want to spend more time on the utility function, so I'll give you another chance to complain. So the probability model is a probability model for tumor growth. So it's a probability model for tumor volume as a function of time. There are some traditional models there. One of them is the Gompertz function, which is usually characterized as a differential equation, which implies a growth curve that is indexed with two parameters, A and B. That phi here is just the ratio A over B. On the next slide, I'll have a picture. So this is simply a parametric curve that is traditional for tumor growth over time. And then we still acknowledge that that parametric curve is certainly just a stylized approximation. What we really see is bound to be slightly different, so we make it a stochastic differential equation. And here's what you get to see. The red guy is the Gompertz function. The black guy is an actual realization once we add the noise. And all I want you to take away from here is that the tumor growth model is indexed with three parameters, A, B, and sigma. This is a traditional model for tumor growth. You could plug in anything else you like. Yeah? That was a traditional model for tumor growth for one patient. We have many patients. So what we are going to do now is we are going to extend it to a population model. So the A, B, sigma get an index I for the IF patient. And we want to have different tumor growth, hopefully, for patients under treatment and patients under placebo. So I have A and B indexed with 1 for treatment and indexed with 0 for no treatment. The notion is that a patient who is randomized, so a patient who makes it to the first step and continues in the randomized second step, will initially be subject to the parameters AI1, BI1, and sigma, because initially everyone is treated. And then in the second step, when that patient might be randomized to placebo or to control, whatever it be, then he or she would be characterized by AI0, BI0. So two sets of parameters for treatment and control. Otherwise, there's nothing to compare, right? Just a minor simplification. It turns out that if you want the tumor growth under treatment to be strictly less than tumor growth under control, strictly less in expectation at least, then you get it exactly if and only if the AI1 is less than AI0 and the B's are the same. The only thing I want to point out here is we'll simplify life and there will only be one B for each patient, yeah? And I think that's all I want to tell you about the probability model. Last thing, in this particular model with these parameters, I introduce a summary psi. So psi is simply the treatment effect. It's simply the difference between the parameters under treatment and under no treatment. So that's all about the sampling model. It's really nice. This was really all Lorenzo's doing, yeah? And I like it, but it's problem specific. Like any different application needs a different one.
So you just have like a single population model for the overall population?
Yes.
Like, so you said that there is like some populations which are susceptible to the treatment and those which are not. So it seems like there might be two clusters or more clusters.
Good point. So you might want to argue that that population model should itself reflect heterogeneity and maybe be a mixture. Or in particular, so what I really talked you through so far only is the sampling model. conditional on assumed parameters. I told you how we think that the tumor volumes arise. What I still need now is I need a random effects distribution. That's what you are bringing up essentially, right? I need a probability model that characterizes how these parameters are distributed across patients. Honest answer, we just use a log normal. Ideal answer, we could have used some mixture here too, yeah? My guess is it wouldn't make too much of a difference, although if I remain true to my initial thoughts, we should do a mixture here too. And then the model is completed with straightforward priors because if you notice, we actually integrate the parameters, so we need a prior. Yeah?
Are you saying that you don't have heterogeneity in your model?
Honest answer, yes, that's what I'm saying.
Okay.
But you're saying the patients are not identical.
Correct, but I assume that they all arise from a unimodal random effects distribution. Their parameters arise from a log normal distribution. And I could have been slightly more sophisticated and taking a mixture there, or going semi-parametric. Would make a lot of sense. Especially since you have you might have quite a bit of data depending on the protocol, right? Like you might observe tumor volume repeatedly on each patient. So it could be done, we didn't do it. There's also an issue, there's also always the contrast between your design model, which is a bit stylized and simplified, and your analysis model. So you might want to do the analysis with something more sophisticated. You're taking me too serious, yeah? So there is a notion of heterogeneity, but we are only taking it serious to a point. So now we have a probability model. I advertised that I'll proceed with a decision criterion, and here it is. The decision criterion is that we obviously incur a cost, like there's a cost to recruiting patients, and there's a cost to keeping patients in the trial. So that's not much of a, if there were only cost, we wouldn't proceed. Fortunately, there is a potential huge golden nugget at the very end of the game. We are proceeding with the trial for only one reason. We are doing the whole thing because there is a chance at the very end, at time t2, we might see a significant treatment effect. And if we see that, that's victory. And that's the reason why we go through the whole thing. So in plain English, the utility function is a sampling cost for enrolling and keeping patients, plus a huge payoff if we get a significant test for comparing treatment versus control in the very end. And all I have to do now is put numbers to that. The sampling cost is easy. We assume there's a recruitment cost in the first stage, a recruitment cost in the second stage, which is presumably less because you're just continuing with patients who are already in the trial, and cost per time unit of keeping the patient in the trial. That gives us a cost function that is just a linear function of cap n is the number of patients that you initially enroll. Small n is random. That's the number of patients who pass the first step selection. And T1 and T2 were just the lengths of stage 1 and stage 2. Choose here is the second part of the utility function. In the end, I'll just add them together. The payoff at the very end of the trial, but here we simplify things. We assume that at the very end of the trial, you analyze the data just by a simple frequentist hypothesis test. So significant outcome simply means that your test statistic is in the rejection region. So RD of X is just whatever is your favorite test statistic. And then we still use a weighting. Do you remember that the psi, do you recall that the psi was the treatment effect? So then we use a weighting with the estimated size of the treatment effect. This should really be a psi sub n plus 1, like the estimated size of the treatment effect for a future patient. Means the more effective the thing, the higher the reward. And for the test statistic, for example, we could use simply a test for independence of treatment and stable disease. So just look at the binary indicator at the very end, stable disease or not. I forgot to mention on the slides how we define stable disease. Could be something as simple as stable disease at the time t2 might just mean less than 30% increase from time t1. So just something very, like if you see the data, you can simply check true or not, yeah? And then the utility function is just a combination of the two. And recall, we would love to maximize the utility function, but short of an oracle, we wouldn't know those two random variables phi and x. Phi we never get to see, x we'll eventually get to see, but we have to make the decision up front. So what we should do by expected utility maximization, optimize that criterion in expectation. And that's exactly what we did. And if I had had more time, I would have talked you through some nifty little games to do that maximization. And we are setting the hyperparameters, like you have to still set things in the model. And doing all that, you can actually come up with an optimal design. So in a particular example, we are finding the optimal design is characterized by sample size 75 and these two times T1 and T2, sorry. And the figure here shows the expected utility surface cut at the point of optimum. If you cut the expected utility surface at the point of optimum, then as you vary the n, you can see how the expected utility changes as you vary the T1 and the T2. And the thing is actually almost unusually sharp. It's of course, you have to interpret a bit with a caveat because notice the scale on the vertical axis. But still, it's quite a decisive point of maximum, which is perhaps characteristic for these designs, because if you get it slightly wrong, you can actually mess it up, yeah? As was discussed in some recent papers. And that's all I wanted to tell you. It's kind of, so in summary, those random discontinuation designs are a nice context, a nice setup to do optimal design, because it might really matter, yeah? Like if you just eyeball the decision, you can get it really wrong to the point that you might be worse off than with a simple upfront randomization.
Thank you very much. That was the first hand I saw. Yours?
You can ask me in Houston.
But I'm sort of curious. You've got three parameters, so you've got N, T1, and T2. Should there be a parameter for the proportion of the population you expect to be susceptible? If I'm building a molecular agent, it's typically targeting a malformation that I know is, from previous data, may be present in 40% of the tumor patients. If it's rare, then the screening may be costly or something.
So two answers. Quick answer, no, because you don't get to choose what percent of your population is susceptible. But longer answer, of course, I get to choose what they call stable disease. So this, I didn't tell you that, but stable disease at the end of the first step is actually defined as between 70% and 130% of initial tumor size. And you could choose also the size of this window. So we could have made the design one step more complicated by actually choosing that criterion. The actual characterization of the patient population, who is susceptible or not, that is stuck in the hyperparameters. So we can only quantify our uncertainty about it, but we can't choose it, right?
But it's a technical point. I mean, the Fisher's exact test, which you throw in at the end, has certain very strict independence assumptions. How do you know that your decision rule has not destroyed the assumptions required for the validity of Fisher's exact test?
Good point. Use a different test. No, sorry. I don't. I mean, a good point. I just tried to put something that looks easy enough, just with a binary response. What you should probably really use is the entire repeated response vector. For example, what we could simply do is we could simply make a hypothesis test on the A. Remember, the A parameter was the parameter that could be interpreted as, so A1 minus A0 could be interpreted as a treatment effect, and that's probably smarter. Agreed.
Last question. Yes.
And in your utility function, shouldn't the payoff be bigger if the subpopulation selected for continuation is bigger?
That would be a very reasonable thing to do. So like you say, from a marketing perspective, if you can sell the thing to more people, you win more. Very reasonable. But I mean, the important thing is, I think it's sensible to get into that kind of discussion, yeah? Like rather than writing, there's a lot to be said also for writing down stylized criteria like the optimality. But the alternative is that you actually think about what's the purpose of carrying out the whole thing and what's the consequences, and then we can start talking about do you want to talk like from a marketing perspective or from the patient perspective. Did you notice that the utility function had the estimated effect? Means the stuff that you get to put on the label rather than the true effect, which is the actual benefit to the patient. So those are choices you make, yeah?
Well, thank you very much. I'm sorry we have to stop this discussion now, but during the lunchtime there's plenty of time for continuation. So thank you again.